All right. So um, each semester is a little bit different. And this semester, we actually kind of have an extra day where today would have been the review and we only had one modulation day, but we actually kind of have 2 days of review. But I've been looking through the notes and the book example and modulation, the simple concepts of modulation aren't that hard. What the book is trying to do is show you a realistic system, and then all of a sudden it's very easy to get lost in the weeds. And I wanted to try to simplify this so that you can see how modulation or radio transmitting and receiving is really something that we've kind of been doing all along, right? With the Fourier expansion and analysis and transform. But when you start getting into realistic amplitude modulation and a whole bunch of other things, it's really confusing. And I have to admit to that. As a result, I didn't like the notes from last time. And so for module 28, okay, I went and added things. All right. And that I'm just telling you that they're here, and then I'll go over it. But pretty much that remains the same. But then I actually have a modulation example. I even have an actual figure here, right? And then I went and did an LT Spice example with 2 data channels. And I'm going to explain this later, just using straight LT Spice rather than read these slides, but it'll be in the video, but all the figures are in fact here so that you can follow along. And then something else I added was some things about pulse width modulation. And I came up with some Python code that would take a filter, right? You can notice this in the Bodhi plot, but also it'll do the pole 0 response. And then I have a kind of a repeating pulse wave if you were to zoom in on that. And then you see what looks to be like a step response, right? Except it's only going to 0.5. And if then you were to zoom in, you'd see a little bit of ripple. And then it goes back to 0 because this turns off. All right. What we did in lab is we just kept it completely in the Fourier domain, and where this is kind of a Laplace simulation where we start with the signals at 0 and then we see them evolve over time. These signals don't exist for all time. But this part here where it's flattened out, and if I zoomed in on that and said it was forever, it'd be the Fourier domain. All right. And then I'm just moving that filter back and forth, and you can see different ripples and whether it's 4th degree. But then later on, there should be, I think I put it in another place. I have some other files that kind of do the same thing that show you, if it's out of control or not. All right. Okay. So I want to just come back to modulation. And so we have 2 data signals, right? And in that LT Spice, I'll show you what those are. All right. And it's essentially a chirp signal, except this is at a faster frequency. All right. So that's the data we want to modulate. And so that's what's coming in here. And this is a mixer, which is multiplication. And that's a sine wave, right? At 10 kilohertz. And then I have another data stream, and this one's at 50 kilohertz, right? And we multiply these together. And so it's actually modulated at that point, right? And then it goes into the air as an antenna, all right? Now, all's we're doing, right? And now rather than write out data, I'm just going to say X and I'll call it D, right? If I multiply that by cosine 2 pi 10 kt, right? That's what I get. I'm not going to show that. Well, I'll show it here. Because the carrier frequency is so much high, it takes forever for it to plot this out, right? And what I do is that when you, if I take the Fourier FFT of that, you can see two peaks, two delta functions, all right? And then this is what it looks like, not only when I've added it, I've modulated each signal, but I've added them together. Again, this takes a long time to plot, so I'm not going to do that live, all right? But what this antenna is doing, right, it's actually a summer, right? Because these two channels are broadcasting at the same time, right? So there's this summer inherent, right? Everything being transmitted is summed in and the antenna picks it up, right? And then what we do is we pass it through a bandpass filter, right? Now, how is it a bandpass filter? Well, that's a high frequency, middle, low, and a cross means no low, another cross means no high. And so it's a shorthand that it's letting middle frequencies go through. And we're trying to select 10 kilohertz. All right. And so if there was no other channels, right, and I just kind of fed that back in, well, I wouldn't need a bandpass filter, right? I could filter it in straight here. And if, on the other hand, if the bandpass filter is perfect, well, it is like feeding it straight in. And then I multiply it again. Okay. And now, this you might notice is cosine squared, which is like sine squared. And so when we did the Fourier expansion of that, right, we got, something at DC and something at 2 theta, right? If this is frequency, all right. Now, you can just use the trig identity, right? But this really turns into 1/2 and okay. So this is our original signal, and it's just multiplied by half, and then it's multiplied by this cosine, right? So this I don't want, right? I want this. So I pass it through. A low pass. All right. And that's really it. Now, yeah, if I take xt times cosine 2 pi, and now I'm going to call it f carrier, right? And I take the Fourier transform of that, this becomes xf, right? This becomes convolution, and this becomes all right. So this is now all in the frequency domain. These delta functions, right? So now if that's 0, and xt just has some frequency information, right? And here are my two delta functions, right? Where I'm at plus or minus fc, and then I convolve it, right? That means I move this across, and the convolution of a delta function, right? Anything convolved with a delta function is, in fact, you get the function just scaled and delayed, right? So this leads to okay. So let's go back a bit. Right. So I'm just going to call this like, this is the first thing, right? And this is the second thing. And this is the third thing, right? So that is really xf, which is the transform of xt, right? This is x carrier f, right? But it's a delta function. So it's a cosine. So you get these two delta functions, right? And they're spread apart, right? And then I just convolve them. And so this is coming out of the antenna, all right? Okay. So now maybe we can say that's one in the frequency domain, right? This is two in the frequency domain. And then here, after it's modulated, that's three. All right. Now, just to go back, we actually have more than one channel here, right? And so channel 2, channel 2. All right. So now they're mixed, right? I mean, they're added, they're in the air. Now the antenna, right? We need to get back our original signal, right? And so how do I get back that original signal? I only want one frequency range, right? So I just draw a bandpass. Now, yeah, that we have our negative frequencies and our positive frequencies. Normally, we're only dealing with that, right? So that's why I get a bandpass, right? But the frequency is still here, right? So I multiply it again by the carrier frequency, right? And what I get, and this is where it gets a little hard to show. I get the original data, but I also get my high frequency data at 2 FC plus 2 FC. All right. So now I've got back my original data centered at 0. This is my original data, but I still got this, right? How do I get rid of it? Well, because I've got positive, negative frequency, I kind of draw it around the center, right? But, you know, if I wanted this, I would draw a low pass around it, okay? So this is the signal modulated, and now this is, so if the modulated equals XF, the original data, convolved with 1/2 delta F minus FC plus delta F plus FC, right? That's modulated, right? It also, you know, goes into the antenna, right? And then, you know, you could say noise is added, right? But when I'm just going to draw a rectangle around this and just say, I'm going to do a bandpass. So now, no noise. So I'm right back to where I started from. You know, maybe I have to multiply it. It's attenuated or something, right? So then it goes into that other multiplier, all right? So XF 1/2 delta F minus C. All right. So this is, so even though it went through an antenna and noise was added, if I have this perfect bandpass filter, I'm right back to where I started, right? I'm right back to modulated. Then I multiply it by a cosine with the same properties. Okay. Now, I'm sorry, I should say convolved. All right. So here's the thing. This is where it gets into kind of a bit of a mess. But if I multiply these through like FOIL, right? Convolve a delta times a delta. Well, that's going to be a delta. And then I sum up the delays. Okay. I'm convolve this with that. And these FCs cancel out. Then I convolve this with that. And again, the frequencies cancel out. Then I multiply this plus that, and I get delta F plus FC. Oh, and excuse me, that's 2FC on either case, because there was minus FC is 2FC, plus FC is 2FC. Sorry. Right. Now, there happens to be two of these, right? One of these and one of these. And so in the end, I get XF convolved with a delta function. Right, plus so anything convolved with a delta function is itself, right? So that's how we get our original data, right? Okay, this bit right here is this. And then I have my two delta functions at 2FC minus 2FC, all right? And so that's what's going, it takes a lot of thing to show, but really, right, the identity of cosine squared, right, is 1/2 plus cosine 2 times the original angle, all right, or frequency, right? And so then we just have to, you know, do our low pass filter, and we get rid of that. All right. So quickly back to LT Spice. All right. Here's my modulated data. Here's channel 1, here's channel 2. But notice if I zoom in on it, I can see that mirrored original data on superimposed on the channel. But look, like this, under this scale, it almost looks like delta functions. You almost can't even tell, right? And if I zoom in there, there's the other one. All right. So this is the one I want, right? So I put it into the bandpass. Okay. Now notice that's still there, but it's attenuated by a lot. All right. But so here's my original, oops. All right, that's my original data. Can really zoom in on it. It's centered at 10 curves, but it looks just like the original data we've seen. Okay. All right, so that's after our bandpass, but it's true. This is still here, right? So now we're going to multiply this again by the carrier frequency, and that would be D mod, right? And there's our original DC, you know, the data centered around 0, right? But notice we have something at 20 kilohertz. And this is coming from the other channel, right? So we had something centered at 50 kilohertz. And then when we multiplied it by something times 10 kilohertz, we got 50 plus 10 and 50 minus 10. And that's where the 40 and the 60 are coming from, right? We don't want it, but in a way, the fact that it's even at a higher frequency, we just now need to draw a low pass around this, right? To attenuate all that we don't want. And that's the filtered. Okay. Now this, I'm not quite sure what that hump is doing. I have to investigate that. And maybe I just need to push the filter out. I chose 500 kilohertz as a cutoff frequency, but also it could be that the behavioral Laplace time domain simulation doesn't really work. All right. So let's look at our original data and the outputs from the demodulator. And, you know, they're pretty much the same, except this one's attenuated, right? Well, I can just use an op amp and boost the gain, right? And so, right? And this noise here at the beginning is showing up in that plot, the FFT. And yeah, it's just, it's attenuated. And I think all I have to do, if I recall, is multiply it by 2. And I'm getting about the same thing. So that's really it. Okay. You have to multiply it by a signal, right? That puts it at the carrier frequency, right? Things get added in transmission. So you use a bandpass filter to recover that original signal multiplied by a cosine, multiply it by the original cosine, and then you actually get back your original signal plus some high frequency things you don't want. And then you do a low pass filter. Now, the thing is, you know, real communication systems are more involved, but they're all doing this kind of thing. Okay. So that should be a lot easier to understand. All right. Any questions?
Is the FC the cutoff frequency?
It's the carrier frequency, and the channel in our example is 10 kilohertz.
Oh, I see.
Yeah, I just couldn't draw. It's just the equations get so long when you use the variable names that I would be here forever. But yeah, it's the carrier. But, you know, here's an interesting thing. Is that this symbol here, it's called a mixer, but that is the multiply symbol, because that's what you're doing, right? And there is a multiplier part, the AD633, right, from Analog Devices. I'm not going to show you all the pins, but you have an X, a Y, and a Z, and it's X times Y divided by 10. All right, now there's other things that go in there, but you know, that's the function, right? And you know, I thought, well, to see if I have a good multiplier, just tie these together, and I'm going to get X squared divided by 10. You know, start off at -1, go to +1, right? and I should get x squared. And then I can kind of curve fit to see how well a multiplier I'm getting. But what actually they do is they put in a cosine, call it let's just say 10 kilohertz, right? So now you put in a cosine, right? Well, we know just from the trig identity that we should really get 1/2 plus 1/2 cosine 2 pi and I might be wrong, that might be a minus sign. I'm thinking that's a minus sign. 2 pi times 20 kilohertz times time. All right. And then they plot it on an FFT, which it's like Scopy or anything, right? And they look, right? There's 0. Are you getting a half? And then there should be something at a half at 20 kilohertz. That's if it were perfect. But things are never perfect. And so there'll be these higher order harmonics, right? And what they do is they compare the magnitudes of these harmonics to the harmonic that should be there, and it's called total harmonic distortion. All right. So again, right, cosine squared 2 pi FCT, right, should give me this in a perfect world. And if it's not that, if there's extra things or missing things, then it's not working, or it's not working as well. All right. And so it just seems that this cosine squared business, it really shows up. It shows up in this whole radio thing, right? It shows up in the testing of the multiplier that you are using to make your radio. Now, there are simpler ways to do multiplication and all of that, but the circuitry of this is really beyond the scope of this class. And I don't, it's hard enough as it is. All right. So just like on the Fourier expansion homework, where it's, find sine squared, find sine cubed, right? It's just applying it in a different way. Okay. Now, I have been reviewing questions that will be on the exam ever since midterm 1, but really, and I have sample exams, right? But let's, what is going to be on the exam, right? Okay. So there's 10 questions. The first 3 are from midterm 1. The middle 4 are from midterm 2. And the last 3 are the final. And these show up in Canvas, right? And let's say you originally got an 80% on midterm 1, but you get 100% on this portion of the exam on the final. Then that 100% replaces your 80% on midterm 1. Now, 100% on midterm 1 does not replace an 80% on these 3 questions. The exam is cumulative. What do you know when you have to know everything, right? Now again, same thing goes for midterm 2. And the final, well, the final is the final. And the first question will be system ID from a Bodhi plot, right? And you're going to have high pass, low pass, bandpass, notch, and you have to find omega naught, the gain, and the damping coefficient. All right. Now, regardless of what the question says, no answers are entered into MOM. All right. I'm not going to take points off if you accidentally do or anything like that. Right. But, what kind of filter? What's the order? Omega naught, gain, and that pretty much gives you the transfer function. Okay. And you can find it pretty exactly, even reading it off of a plot. Right. Then we'll have system ID. From a transient, right? And it'll be the same thing. High, low, band, notch. But you don't find it exactly. You estimate things, Is zeta less than 1, around 1, greater than 1, right? Things like that, because I don't like to say things are impossible, but to be able to do system ID from a transient just by doing a graph like the way we do for the Bodhi plot, it just doesn't work. All right. And then the last one is it's like an application of the Fourier, right? So just like that, like I'll explain the situation. You're testing a multiplier and you see this, which thing do you want? Here's a radio. What do you want from here? That kind of classic, here's a 50% duty cycle square wave. You get these things and I say, I want a DC. And you're like, okay, I want a low pass. I don't want that frequency. Okay, I put a notch. I want that frequency. Okay. I do a band. I want all of those frequencies. Okay, I do a high, right? There's examples, okay? But it's some kind of application that if you've looked at the applications and given yourself, you've done the homework to the best of your ability, you should be able to follow along. But it's more essay and explaining rather than it's right or it's wrong. Okay. For midterm 1, it's Bodhi, it's low, it's high, real poles, most likely second order. Okay. And the poles will be repeated 10 times apart, 100 times apart, or 1,000 times apart. Okay. So it's a, the last question here, is it a high or a low? You got to do the Bodhi, the transfer, and the step and plot, right? Thing is you could do problems that could be there that you might not have seen. Is this one, which is an integrator, right? But it's the one where you kind of have to do everything. Now, again, maybe these are it's out of order, but it's like convolution here. Okay. HT equals something. G of T equals something. Find the equation, plot. What kind of filter? Okay. Now, the thing about answering, justifying an answer, what kind of filter, is you can no longer say, well, it looks like it is because that's what it looks like, right? Why is a low pass filter rounding? Why does a high pass filter detect edges, right? We have talked about that when we let S go to infinity, right, that's kind of giving us our transfer function when time equals 0. When we let S go to 0, that's giving us our time response at when T equals to go infinity. And so you can give a very good reason as to why things are going on, right? You can't really use circular logic, okay? DF2, which is really, just so you know, state space. Outside of 110, it's called state space, right? Then we'll have a gain bandwidth type problem. Mass spring damper type problem. And then a control problem. All right. And really, this will be the same generator, the same, the same problem generator. I have different problems, but it's like the same generator. And I'm pretty sure it's like the same random questions will be there. So you won't get the same one, but you'll get from that bank. Okay. And in fact, the Bodhi plot is the same generator. This one would be, I'm going to change some of the equations, but it's effectively the same, right? And then this is the same generator. All right.
What does question number 2 say again?
Convolution.
Oh, convolution.
Sorry.
Professor, when you mentioned,
Now, really, if you look at all my sample exams, you can see what it is. I'm just trying to give you a high level view of it, almost like telling you the algorithm I'm using to generate the exam.
Professor?
Yes, sir.
Oh, okay. When you mean same generator, do you mean like the same generator you used for our previous midterms?
Right. So I use my open math, with various random numbers and plots and figures, right? and I have algorithms that generate the equations. So I just call that an equation generator, right? So I have, Bodie plot generators where it's either low or high and all the poles are real, right? And so you have different gains, different poles, right? And different pole separations, right? For question 2, in general, the input signal is a step or a rectangle, right? And the transfer, the impulse response, it's either a high pass filter or a low pass or some kind of approximation, right? So, right, this is 1 over RC e to the minus t RC ut, which is the impulse response of a low pass filter, right? But if I do this approximation, oops, excuse me, right? Well, it kind of looks like that shape. So it's going to act low pass. Even a rectangle is low pass like. Okay. Even if I do this, right, that'll be low pass like. Yeah, so Brandon, it's 10 points per question, yeah, or 10%. But in your Canvas, there's under exam, there's actually 3 separate grades inside one grading block of exam. Okay.
So
Yeah. Oh, and I just wanted to finish a thought here. Sorry. So to turn those into high pass filters, I just add a delta function in the opposite direction. Now, all of these now would be inverting high pass structures, right?
A
But
quick question.
yes, Justin.
What does the equation for the inverted high pass for the inverted delta function look like?
So this is the transfer function of an inverting high pass. What that would look like is minus delta t plus 1 over RC e to the minus t over RC ut, which would look like this. This, oops, the magnitude would look the same, but then the phase
Oh, I see.
so
So that's how.
you get it? Okay, great.
So that's how you get the inverted delta.
Yeah, you just draw it in the opposite direction. Sorry, I misunderstood. Good question.
So you just basically put a negative sign for the transfer function, or
Yeah,
that's it. You put a negative sign on the transfer function.
right. Now, if you do partial fraction expansion and all that, it comes out.
All right.
Okay.
Yeah, I got a question.
Ask, please ask.
Okay, I have a general idea, but in concrete terms, what's the precise definition between the impulse response and the step response?
Okay. So, and that's a good question. Okay. But basically, I have a system. I put in, so let's just say xt equals delta t. And I have ht, right? Well, that whole system really is xt convolved with ht, right? So I have a delta function coming in, I have ht, I'm convolving, anything convolved with a delta is in fact your original thing, and it's what you get when you input a delta function, otherwise known as an impulse. Now, if x of t equaled u of t, a step, right? Well, out comes the step response. But notice this ht and that ht are the same because when I put in a delta, I get the same thing. In this case, no, it's, I'm convolving it with the step. And then the ramp is the same thing, except you're inputting a ramp.
Oh, now I think I get it.
Yeah. And so people were confusing the impulse and the step shapes, right? On that, I think it was question 4 on midterm 1. So if this is the step response of a high pass, but it kind of looks like an inverted, right? But really, this is the step response of a high pass, but this is the impulse of a low. And so you have to know what's being input. So if I put an input into a low pass, I get this. If I put a impulse response into a high pass, right, that's what I get. And so people were kind of confusing the two. If I recall, that was probably one of the more common mistakes. Okay.
Thank you for clearing that up. Because of that, I was never 100% sure what the train or what a high pass filter and a low pass filter looks in the transient and domain.
Yeah. And remember, the Laplace of the impulse response is in fact a transfer function.
Okay. Yeah, but it's important to mind the difference between that and the step response, which will give you two very different things.
Mm-hmm.
Now I get it.
What happens is we spend so much time in the Laplace or the Fourier domain that we even forget the time domain exists. And if you think about it, right, here's the FFT, and I want to show a cosine. Okay, that's it. See how quickly it plotted? It's a delta function at the things, at the carrier frequencies. Well, now what I'm going to do is now, what if I want to plot that sine wave over 500 milliseconds? See how long it's taking? Right? Sometimes my computer locks up doing it, waiting. because that's just a heck of a lot of data, right? All right, I can't take it anymore. So now, yeah, if you recall, right, even I'm forgetting the module names, but the day after the exam, right, of midterm 1, I kind of went through the most common mistakes and kind of a guide to the answers. Same for midterm 2. All right. So if I were making my study guide, right, I'd probably go there. Right. Now, I'm not trying to trick anybody, right? When I make a book open note, it's just so that if somebody uses something that, if it is closed book, closed note, right? And then somebody's using something they shouldn't, then I have to prosecute that. And it takes forever to deal with that. But if I don't, well, then it's worse than having no rule at all, right? So by making it open book, open note, it doesn't mean that every resource out there is in fact authorized or correct. All right. There's a faculty community on My Open Math, and some are saying that they put bad solutions on Chegg so that they can tell where they got it from. And then to me, it's kind of a trick. Like, if you got time for that, you got way too much time in your hands, right? Now, some people encode their problems so that they can go on Chegg and find out who uploaded their copyrighted exams. All right. Which, well, I guess when I have time to do that, I don't know what I'll be doing because I'll have too much time. All right. But it doesn't mean that but here's the thing, just because something's on Chegg doesn't mean it's correct. Right. And this is happening in 98. And what I think, what puzzled me is that why would somebody go to Chegg when usually the notes in 98 or 110 are there and are actually authorized? And if you showed me, hey, professor, here's your notes where you had it backwards and I answered like you said, oh, I'd have to accept the answer, right? But no, there's like these bad solutions out there or bad sources of information. All right. The only thing I can think of is that when you're running out of time and you do a Google search, maybe Chegg comes up because Canvas isn't searchable. And I don't even think my notes are searchable. I think I would have to publish it to the web. And they're not exactly ready for prime time. But really, you got to prepare for these exams, okay? In that, get your equations and everything there, and make sure you have trusted sources of information, trusted sources of non-interactive information. Okay. I use the phrase interactive because maybe one day there'll be some artificial intelligence that can be a helper, and that'll be cheating. Okay. Any questions about that, or, really anything? Oh, sorry, there's a few chats. The dirty. Yeah. I mean, the thing is I'm reading your answer, Emmanuel, about Chegg. It's this kind of struggle. Professors want students to do the work themselves, but really, we all learn by following examples. And, so if there were examples already published and just tell the students, follow it and do it and prepare for exams that way. But sometimes if you do that, a lot of times you don't get enough people doing the homework that they should. And professors have to assign points for things, because not only are you taking 110, but you're taking a whole lot of other courses. You are working, you're taking care of your family, pets, involved in politics. I know people have a lot going on. And so sometimes professors have to make things worth points, even though studying for the exam, right, is getting your points. But that's just the philosophy of it. I don't mean to monologue.
Professor, that it is all 10 questions in MOM exam.
Excuse me?
There will be all 10 questions in one MOM.
So the exam will be delivered in MOM, right?
Yeah.
And you'll get the exam and then print out a copy, PDF or whatever, so that if something happens to your internet, right, you have it and you just keep working. But you don't have to answer any questions in MOM, right? I'd prefer it if you didn't. Okay.
That's the file upload.
For the final, yeah.
Okay.
Yeah. So really, it'll be just like midterms 2 protocol, right? The
Yeah.
reason why midterm 1 you can answer in the answers is I naively thought I could program the whole course that way. And nope, it's beyond me. And actually, it might not be a good idea. I think people were more relaxed with here's the exam delivery, and then you just do it and scan it, and that's it. Because I think I graded the exams faster than with the automatic grading. I don't know. Oh, good question, Derek. 110 lab and 110 are completely different courses, where 118 and Maddie 153, the lab is embedded and they might be worth 25%, I forget. So 0%. However, everything you learned in lab is a way to check your work for your exam. So if you had everything all prepared, it could be worth 100% of the final, if you follow me.
So, Professor, there will be total 10 questions in MOM.
There'll be 10 questions, yes.
Okay.
Now, I forget, Justin, it might have been you. You had a question on Monday, and I don't think I ever answered it, about power supplies or something in DC. Was that you?
Yes, it was for like homework 13.
All right. Do you want me to answer your question?
Sure, yeah.
What was your question? I just kind of have the gist of it. I don't remember it.
It was like what was the power source DC supposed to look like in LT Spice? The one you gave an example in the 60 hertz clock.
Okay. So, I mean, I gave you the LT Spice file, right? So what do you want me to show you?
I just want to see what the voltage source look like in format, like say sine, or is it pulse?
Okay. So listen, I'm just going to start, and if I'm on the wrong track, please let me know. Okay. So we're going to start off in the time domain. Okay. And this is my interpretation of a sine wave with a V peak, right? And it's either 50, I think it's 60 hertz in the homework. All right. Now I need to convert this to DC, right? Well, what does this look like in the frequency domain?
Is that the half wave?
No, this is the cosine.
Oh, yes.
Well, all right. Assume I've delayed this so it's a cosine, okay?
Oh, yes.
Because now they'll both point in the right direction, okay? So that's the frequency domain, right? That's the Fourier expansion. Although when we do the FFT, right, we're only looking at this part. I'm not bothering with that, okay? And then this would just be VP. All right, since we were doing modulation, I was showing the negative and the positive frequency. So the thing is, right, I need something at DC. Okay, so the thing is now this is like design. Rather than tell you this is what I've done, you got to make it happen. So it's a lot harder. Okay, and there's two ways. Mathematically, I can do that. I can do the absolute value of cosine, or I can do cosine squared. Okay. Well, the absolute value of cosine is the full wave rectifier, right? If I have one diode, I have the half wave rectifier. If I have four, I have a full wave. And so taking the absolute value, right? So what I'm just gonna change colors and say, actually, so I'm going to take the absolute value of this. All right. So now I can do this by eye, right? If this was at 60 hertz, well, it's repeating now twice as fast. So I'm going to have something here. Sorry, I'm at a bad angle today. So I'm at 120 minus 120. But notice, just by looking at it, there's no negative part. And so I don't necessarily know what it is off the top of my head. But there is now a DC component. And you can see that it's not a pure sine. Like if I do cosine squared, there's a trig identity, right? And you get 1/2 plus 1/2 cosine twice. No, this has an infinite sum that make it up, but you get a magnitude of 0.707. So what would be the circuit? The full wave rectifier made out of the 4 diodes. All right. So that's, so now, and that's the VP. So that's what it looks like. Okay. Well, I want, so remember, what did I want? DC. So 0 hertz, right? That's otherwise known as DC. But people will call this DC as well, because even though it's changing in time, the current would only be flowing in one direction, right? It might go to 0, but they call this is like a DC signal, even though it's changing in time. But most people say there is no frequency component. It's flat, right? So what do we want? We want the DC part. Now, be careful. It might look like I did a bandpass filter here, right? But this is symmetric. It's really a low pass filter. So there's my 0 hertz and there's my 120. I want a low pass to get that. All right. So that's, so then if I just had a, oops. So if I just had a constant voltage, right? I would have something at DC. And so that's what I would want. Now, of course, there'll be ripples and noise up here. Nothing is perfect, but you just say what level of ripple is acceptable, right? So this part is the absolute value, and this part, we use a low pass to turn it into that. So is that what you were thinking, or Justin? Or did you have to go?
It's kind of like what I was thinking, but not exactly. I was like on the LT Spice, like.
You wanted to see it in LT Spice?
Yes.
Oh, okay.
That's a 60 hertz power source.
This example was 50. Okay. So this is coming. So that's my sine wave, right? And that's my delta function. And when I convert it from RMS to amplitude, I should get my 155 peak to peak. Okay. So this is just a transformer. That wasn't really part of the question. I went above and beyond what you needed to do. Right. So here I have this diode is the full wave rectifier. And so it should be making my absolute value. Right. It's not perfect. Okay. And it takes time for it to work, right? But and it's not a perfect absolute value because I'm using real diodes, right? But you can see, right, that that's working. And then there's my low pass filter. Oops. Oh, so okay. So here's my V1. Right? That's my sine wave, and it has some harmonics, right? But then this is my low pass filter, and you can see that that part is now gone. Now, yeah, it's not regulated, so I put it into a regulator, right? And so now I have a constant, which I don't even know what the FFT will do, because LT Spice's FFT gets rid of the DC part. Okay. And now here is, so this is the output of the low pass. Then here's the output of the regulator. And then here, the clock, basically I'm just have a sine wave that's reduced. Okay. And I put it into just an op amp with a power rail. And it just tries to go above the rail and turns it into a square. Okay, is that what you wanted? Oh, Karan, you too. Take care.
Yep. I was looking for it.
Okay, all right. That might I thought I did that in the video, but I forget. Okay, I know you got to go to 112, but try to bring your questions to Monday's thing, right? Because I don't know what you're struggling with. And so if you let me know, I can help you.
All
Okay,
right.
everybody?
All right, have a good day.
All right, take care. Thanks for coming.